Hello everyone, I'm Norman Wahlberger and welcome to Algebraic Calculus. In this lecture we're going to pin down the sums of powers formulas that go back to Faulhaber and also to Jacob Bernoulli. So basically we're interested in this kind of series. Sk of n equals 1 to the k plus 2 to the k plus all the way up to n to the k. In summation notation, sum I equals 1 to n of I to the k. And the exponents here, the k's, are natural numbers 0, 1, 2, 3, etc. And we're interested in trying to establish or find a formula for these kth powers, running from 1 up to an arbitrary natural number n. Now, we know, sort of classically, that there are these wonderful formulas for the cases k equals 1, 2, and 3. So the sum of simply the natural numbers themselves from 1 up to n, 1 plus 2 up to n, is n times n plus 1 over 2. And the sum of the squares, 1 squared plus 2 squared, all the way up to n squared, is this, n times n plus 1 times 2n plus 1 over 6. While the sum of the cubes, 1 cubed plus 2 cubed, all the way up to n cubed, is this thing squared, namely n squared, times n plus 1 squared over 4. Now, in 1631, Johann Faulhaber wrote down a whole bunch of extensions of this. So he investigated what happens when you consider the sums of higher powers of natural numbers. And he, in fact, wrote down the first 17 sums. And included there were these next ones. So S4 of n is the sum of the fourth powers. That turns out to be this polynomial in n. The sum of the fifth powers looks like this one. The sum of the sixth powers looks like this one. Now these formulas are actually very important, and we're going to be putting them to use in a lot of different ways. So they figure in calculus in a number of interesting ways, and they're actually quite interesting, just sort of independent interest, even if they weren't as useful as they are. So what we want to do today is we want to have a look at the historical approach to these polynomials, largely centered around the work of the genius Jacob Bernoulli. But then I want to actually introduce a novel way of looking at them, which combines insights of Blaise Pascal with the power of modern linear algebra. And we're then going to be able to formulate a, I think, simplified view as to what these polynomials really are. So at the end of the lecture, you are going to have the technology to be able to write down, with the aid of a computer, in just a few minutes, all of these polynomials up to some reasonable amount, say up to like 10 or 12. You'll be able to do it very quickly. And so it's very, very powerful technology that we're introducing today. So a very important ingredient in understanding sums of powers is Pascal's array, which is Pascal's triangle, just arranged in a perhaps somewhat different way. So here we have this array where we have the usual rows of Pascal's triangle left justified. 1, 1, 1, 1, 2, 1, 1, 3, 3, 1, 1, 4, 6, 4, 1, 1, 5, 10, 10, 5, 1, 1, 6, 15, 20, 15, 6, 1, 1, 7, 21, 35, 35, 21, 7, 1. And you'll all, I hope, recognize that these are just the coefficients that you have when you expand an expression like a plus b to the n in terms of powers of a and b. So for example, if you expanded a plus b to the fifth, then you would have something involving these coefficients here. 1 times a to the fifth plus 5a to the fourth b plus 10a cubed b squared plus 10a squared b cubed plus 5a b to the fourth plus 1b to the fifth. Okay. Now, the ijth entry in this table, and we're going to index the table, perhaps a little bit interestingly, starting from 0. That turns out to be sort of a sensible thing to do. So we'll call this row 0, row 1, row 2, column 0, column 1, column 2, and so on. And this entry will be denoted by I, and this one by J, in the usual language of linear algebra to denote positions in a matrix. So this one here, for example, is the 3, 2 entry. It's when I is equal to 3, and when j is equal to 2. Okay, and the ijth entry is a binomial coefficient. It's usually denoted like this, with this special bracket denoting a binomial coefficient, and it's written I over j, but read I choose j. And the value of that by definition is I factorial over j factorial times I minus j factorial, where of course j factorial means the product of all the natural numbers from 1 up to j. So 4 factorial, for example, is 1 times 2 times 3 times 4 is 4 factorial, was 24. Okay, so this array turns out to be intimately connected with the sums of powers problem, as was realized by Jacob Bernoulli. And he was one of this very influential family of Swiss mathematicians. Okay, so the columns of this Pascal array are what are called figurate numbers. So if we look down the columns, here's just ones, and here's just the natural numbers themselves. And here are the triangular numbers. And the next column has the pyramidal numbers and so on. So these are numbers that have geometrical significance, going back at least to this column here and this one to the ancient Greeks. And Bernoulli realized that the columns of this array have the property that they can be summed easily. That's sort of the critical point. That it may be difficult to sum powers of natural numbers, but it's not hard to sum these kinds of numbers. For example, if we wanted to sum all the elements in this column down to 20, 1 plus 4 plus 10 plus 20, well, that would be 35. And it turns out that that's just the entry that's diagonally below the bottom one. Okay, and that's a key point. So let's have a closer look at that example. If we're looking down this column here where j equals 2, these are the triangular numbers, 1, 3, 6, 10, 15. And they're given by this following formula. They're I choose 2. So I choose 2 means I factorial divided by 2 factorial divided by I minus 2 factorial, which amounts to I times I minus 1 over 2. So for example, if I is 4, then it's 4 times 3 over 2, that's 6. If I is 5, we're talking about 5 times 4 over 2, that's 10, etc. So those are the entries here, and we notice that this is a quadratic expression in I. Okay? As a function or as a dependency on I, it's essentially quadratic. Right? If you expand this out, you get I squared minus I over 2. That's a quadratic expression. That's the dependence as we go down here. Okay, now suppose we are interested in summing this column, say from I equals 0 to 6 of I times I minus 1 over 2. In other words, we're adding 0 plus 1 plus 3 plus 6 plus 10 plus 15. Okay, that is 35. And it turns out that that is indeed 7 choose 3, which is this entry here, which is 35, or 7 times 6 times 5 over 3 times 2 times 1. And more generally, what happens is that this phenomena occurs for any one of these columns, and I want to explain to you why. Okay? So why is it that summing down any of the columns of the Pascal array is very easy, or relatively easy? You just look at the entry which is diagonally below and to the right of the bottom entry of the column you've got. That's almost a direct consequence of the fundamental additive property of the Pascal array. Namely, that if you want to know what this entry is, you just take the sum of the entry above it and the one that's directly to the left of that. So 4 plus 1 is 5. 10 plus 5 is 15. 5 plus 1 is 6. 5 plus 10 is 15. 15 plus 20 is 35, etc. So that's valid across the entire table. Even up here, 0 plus 0 is 0, 1 plus 0 is 1, etc. So why does that explain that property? Well, let's have a look at this column, say here, this one here. If we're looking down here and we're summing all the way up to 1, then it's certainly true that the sum all the way up to there is equal to 1, the diagonal that we get from going down from that one. Now suppose we add one more to this column. We add the 4. So now we're summing down to 4. Well, that means then the total is going to be the previous total, which is contained there, plus the new term. But the array is arranged so that sum is exactly what's down here. Okay, so it will be the case that this whole sum will be equal to 5. And then if we want to add one more, we add this one here. We're adding now the whole column down to 10. Well, that just amounts to taking the previous sum plus the new entry, and that total is, by definition, that entry there, 15. So by a kind of induction on any column, so the same pattern occurs no matter which column you start with, because the top of every column is a 1, and the one diagonally below that is also another 1. So that same argument is going to be working for every column of this matrix and allows us to sum the entries of any column very easily. In algebraic terms, what we're saying is that the sum from I equals 0 down to some, say, value n of I choose j. So this is 0 choose 2, this is 0, 1 choose 2, 2 choose 2, 3 choose 2, 4 choose 2, 5 choose 2, 6 choose 2. That sum is going to be n plus 1 choose j plus 1. So it'll be 7 choose 3. Because here we've been going down the j equals 2 column, so we have to move over to the next column. The j goes to j plus 1. So this realization that the columns of the Pascal array are easily summable is due to Jacob Bernoulli. And with that understanding, he was able to exploit that to find formulas for the sums of powers. His thinking is this: all right, the columns here are polynomials in I. Okay, so we know how to sum these particular polynomials. And so if we're interested in summing a pure power, like I cubed, then what we can do is express I cubed as a combination of these ones. Okay, that's a cubic, that's a quadratic, that's I. So if we write I cubed as something times this, plus something times this, plus something times this, and we know how to sum these ingredients, then we can deduce from that a sum for I cubed. That's exactly what he did to get his famous formula for the sums of powers, sort of extending and generalizing Faulhaber's formulas. Okay, so here's Bernoulli's famous formula, that the sum from I equals 1 to n of I to the k is 1 over k plus 1 times the sum from j equals 0 to k minus 1 to the j, k plus 1 choose j, a number called b sub j, and then the n to the k plus 1 minus j. So this is a polynomial in n, starting with the highest power, which is n to the k plus 1, and then decreasing powers of n. And these then are the coefficients. The minus 1 to the j just alternates, plus minus 1. And this is a binomial coefficient that depends on the fixed value k plus 1 and the j, which is changing. And the b sub j, which is the most interesting part, are these new numbers, which are now called Bernoulli numbers. And they turn out to be a very fascinating sequence of rational numbers. And the first one is b0, which is 1, and then b1, which is minus a half, b2, which is 1/6, b3 is 0, b4 is minus a 30th, b5 is 0, b6 is 1 over 42, b7 is 0, b8 is minus 1 over 30, b9 is 0, b10 is 5 over 66, and it carries on. Now, all of the odd Bernoulli numbers are 0, except for this first one, which is rather special. Okay, but all the other odd ones are 0. And then it really only depends on the even ones. And the numerators and denominators are very interesting numbers, and you can find out about them in Sloan's online encyclopedia of integer sequences, which is a web reference that's going to be quite useful for us as we go through the course. Okay, so you'd have an initial look at the online encyclopedia of integer sequences, and these two sequences, A000367 and A002445, these even Bernoulli numbers. So it's reasonably complicated. First of all, you need the information of the Bernoulli numbers. That's kind of important ingredient. And then there's this lovely but admittedly somewhat complicated formula involving them that allows you to write down these sums of power polynomials. Okay, so we do want to understand these polynomials in a logical way, but I'm not going to go through the derivation of Bernoulli's formulas because I want to present the topic in a different way. I want to give you a different way of finding these Faulhaber polynomials. And what we're going to do is we're going to go back to another great mathematician of the 17th century, Blaise Pascal, who had a certain insight into the same kind of problem. He was also very interested in this kind of thing. And we're going to take some of his insight and combine it with the power of modern linear algebra in what I think is something of a novel way. Okay, so what are we going to do? So the basic idea is we're going to exploit this cute little trick almost of what's called a telescoping series. This is a special kind of series that is easily summable, almost like magic. And it's a series which involves successive differences. And so here's the special case that we're interested in. For k a natural number, let's look at the sum from m equals 1 to some n of m to the k minus m minus 1 to the k. So it's the same kind of expression here and here, and we're taking the difference of those successive expressions. And let's have a look at what it actually looks like explicitly. When m is equal to 1, we get 1 to the k minus 0 to the k. When m is 2, we get 2 to the k minus 1 to the k. When m is 3, we get 3 to the k minus 2 to the k. So it'll continue like that up to the very last term, which will be n to the k minus n minus 1 to the k. And now here's where this telescoping aspect comes in. If we look at this, we see that there's going to be a lot of cancellation. In fact, almost everything is going to cancel out. Because the 1 to the k is going to cancel with the minus 1 to the k in the next term. The 2 to the k is going to cancel with the minus 2 to the k in the next term. The 3 to the k is going to cancel with a minus 3 to the k in the next term. The things which are not going to cancel are the minus 0 to the k that we started with, and the very final one in the last expression, the n to the k. This one here is going to cancel with the previous one, but this n to the k is going to live, and this 0 to the k is also going to live, but that's 0. So in fact, the whole thing just reduces to the simple expression n to the k. So to exploit this, we're going to have to look at how we expand this thing out using the binomial theorem. So the binomial theorem says that m minus 1 to the k is m to the k minus k choose 1 m to the k minus 1 plus k choose 2 m to the k minus 2, and so on, up to the final term, which is going to be minus 1 to the k times m to the 0. So the powers of m decrease, the powers of 1 increase, or actually the powers of minus 1 increase, so it's minus 1 to the 0, minus 1 to the 1, that's why we have a minus sign, minus 1 squared, then minus 1 cubed, etc. Okay, so now if we combine that with what's in here, here we have m to the k minus this expression, so if we take this thing here and we take m to the k minus that, then the m to the k's will cancel, and we'll have k choose 1, which is k times m to the k minus 1, that term there with a plus sign now, and then minus k choose 2, m to the k minus 2, and plus the next one and so on, and we'll go all the way up to this last term, which will now have an additional minus sign because we're bringing it to the other side. So it'll be minus 1 to the k plus 1 times m to the 0. Okay, so we are now going to exploit this telescoping series to see another way of getting at these sums of powers. All right, so here's now the heart of the matter. Here is the expression that we've just established with this telescoping series. And let's define s sub k to be what we called s sub k of n before. The sum from m equals 1 to n of m to the k. So this is the quantity that we're interested in. This is a polynomial in n that is the sum of the kth powers. Okay, the kth powers from 1 to n. And it is a polynomial in n, but let's just call it s sub k. And k runs from 0, 1, 2, 3, etc. Okay, let's have a look at what this formula is telling us now for various values of k. When k is equal to 1, over here we have m to the 1 minus m minus 1 to the 1. So that's just 1. That's 1 inside there. And so this sum from m equals 1 to n is just s0. That's the sum of the 0th powers of the natural numbers. And the right-hand side will be n to the 1, which is just n. So that's something that we know already. When k is equal to 2, this telescoping thing tells us what? So here's m squared minus m minus 1 squared. Okay, from the binomial expansion of m minus 1 squared, this quantity inside here is going to be 2m minus 1. And so we're summing that from m equals 1 to n. What are we going to get when we sum that? Well, we're going to get 2 times the sum from m equals 1 to n of m. That's the sum of the first powers from 1 to n. That's what we're calling s1. And the minus 1 means we're going to get the sum s0 again. So this telescoping thing in the case k equals 2 tells us that 2s1 minus s0 is the right-hand side, which will be n squared. When k equals 3, what do we get? Well, the difference between m cubed and m minus 1 cubed is by the binomial expansion that we already talked about. 3m squared minus 3m plus 1. And when we sum that from m equals 1 to n, we're going to get 3 times s2, the sum of the squares, minus 3 times s1, the sum of the first powers, plus s0, the sum of the 0th powers. And that's necessarily the same as what we get on the right-hand side, which is n cubed. And let's do one more to get the hang of it. So when k is equal to 4, we're talking about m to the 4th minus m minus 1 to the 4th. So that difference is, again, by the binomial theorem, 4m cubed minus 6m squared plus 4m minus 1. And we're summing that from m equals 1 to n. We get 4 times s3 minus 6 times s2 plus 4 times s1 minus s0 equals what's on the right-hand side, which is n to the 4th. And I hope you can see that you could carry this on in a relatively predictable way. What's happening in here is just the binomial expansion, basically, of m minus 1, but it's m to the k minus m minus 1 to the k. It's just this thing here evaluated that we had on the previous slide, but in very specific cases. K equals 1, 2, 3, 4, etc. So in each case, what we're getting is a linear equation involving s's on the left-hand side, and our known power of n on the right-hand side. All right, so to summarize what we just did on the previous slide, here are the 4 equations that we got. S0 equals n, 2s1 minus s0 equals n squared, 3s2 minus 3s1 plus s0 equals n cubed, and 4s3 minus 6s2 plus 4s1 minus s0 equals n to the 4th. And these are 4 linear equations in S0, S1, S2, and S3, and so we can solve them. That's what linear algebra does. It solves systems of linear equations for us. And it does so very conveniently if we write things in matrix form. So here is the matrix form for this system of linear equations, where we introduce a vector, components S0, S1, S2, S3, another vector with components n, n squared, n cubed, n to the 4th. And then all of these equations are represented by this single matrix equation, where here are the matrix of coefficients. And I've just rewritten it a little bit because the S0 comes first. So we're kind of reading from right to left here. So this says S0 equals n. This one says minus S1 plus 2S1 equals n squared. This one says S0 minus 3S1 plus 3S2 equals n cubed. That's essentially this one. And the last one says minus S0 plus 4S1 minus 6s2 plus 4s3 equals n to the fourth. Okay, so now we are going to invert this. In linear algebra or matrix formulation, the way we do that is we take the inverse of this matrix. And then that will allow us to solve this vector in terms of the inverse multiplying that thing. Now, the inverse of a matrix is, in general, reasonably tricky to work out. For a lower triangular matrix like this, it's a lot easier than it is for a general matrix, but it's still some work. But nevertheless, modern computational algebra packages do this kind of computation instantaneously, at least if the matrix is not too big. So our computer easily tells us what the inverse of this matrix is. It's this matrix here. Matrix which is also lower triangular with entries 1, a half, 1/6, 1/2, 1/3, and 0, 1/4, 1/2, 1/4. And so that previous matrix equation can be inverted to give us S0, S1, S2, S3 as this inverse matrix times n squared, n cubed, n to the fourth. And that allows us to just read off what these various polynomials are, because we can just multiply this out. This vector times this is n. This times this is 1/2 n plus 1/2 n squared. This next one will be 1/6 n plus 1/2 n squared plus 1/3 n cubed. And the next one will be 0 n plus 1/4 n squared plus 1/2 n cubed plus 1/4 n to the fourth. And so we can immediately read off what the various s values are in terms of n. So it's telling us that s2 is 1/6 of n plus 1/2 n squared plus 1/3 n cubed. That's an alternate way of writing down the polynomial n times n plus 1 times 2n plus 1 over 6. And this one here is another way of writing down the polynomial n squared times n plus 1 squared over 4. And the pattern generalizes. That's the beautiful thing. We just need to generalize this story by basically just extending this matrix in the obvious way and taking its inverse, and boom, we find a nice formula, not just for the particular value of s that we're interested in, but in fact all of the values of s along the rows of the inverse matrix. So a very powerful technique exploiting our understanding of a little bit of linear algebra, okay, which you can get from my linear algebra course or any other place, just inverting matrices to solve a system of linear equations, really the fundamental problem of linear algebra. So let's have a look at a bigger example. So here is k equals 8. So suppose we wanted s sub 8, the sum of the 8th powers. What would we do? We would write down this matrix. This is actually not so hard to do because it's very close to being the Pascal matrix that we talked about earlier, but it doesn't have that diagonal of 1s, sort of as if we stripped off that diagonal of 1s. So we have 1, 1, 2, 1, 3, 3, 1, 4, 6, 4, 1, 5, 10, 10, 5, 1, etc. But with no 1s, and also crucially, minus signs on every second diagonal. So those entries all have a minus sign, and then 2 down. Those entries all have a minus sign. Those entries all have a minus sign, and so on. That pattern just repeats. But for a computer, it's actually relatively easy to write down the formula for the ijth entry of that matrix, and then you have that matrix there, and then you calculate its inverse. Okay, the inverse of this matrix is this one here. And it turns out pleasantly that this has inside it the inverses of all the smaller ones. So the one that we just obtained in the previous example was this top 4x4 entry there. Okay, so this one here is extending the previous ones. And it gives us all the values of s down to this row here, and that'll be s8. So s8 of n, which is the sum from I equals 1 to n of I to the 8th powers, you can just read it off by going along the bottom row here. So with increasing powers of n, starting with n, minus 1 over 30 times n, plus 2 over 9n cubed, we skip the n squared, minus 7 over 15n to the 5th, plus 2/3 n to the 7th, then plus 1/2 n to the 8 plus 1/9 of n to the 9. And that is a polynomial that Faulhaber would have had and Bernoulli also wrote down. In factored form, which is an alternate way of representing it, it has this expression. But perhaps it's actually nicer to think of it in this form here, which is actually the form that Bernoulli wrote it down in. And as Bernoulli remarks, there's a pleasant pattern here. And basically Bernoulli's formula is telling us that there's actually these Bernoulli numbers appearing down the first column. So if we look just at the first column here, those are particularly important. Those are the Bernoulli numbers, all right? Actually, except for that one there, that was a negative of the Bernoulli number I said, but that's rather special. But Bernoulli's observation was that the entire array here can actually be generated just by knowing that first column if you are willing to multiply by suitable binomial coefficients to get other ones in the associated diagonal. Okay, so in the accompanying notes to the course, we'll be exploring more aspects of this beautiful kind of relation, the Bernoulli numbers, these matrices that appear. There's all kinds of interesting things to learn about this story. But this is the basic framework, the idea that you can calculate these sums of powers relatively directly just by writing down a relatively simple matrix and getting your computer to find the inverse. It's very efficient and something that you can remember. So we are going to be exploiting these sums of power polynomials. They're very beautiful things. So there's much to learn. I'm Norman Wahlberger. Thanks for listening.